Hi everybody, now we want to think about when the area is below the x-axis, what does that mean for what we're doing? And so if we consider this function x squared take 1 between 0 and 1, we can see that the area that we're looking at between the x-axis and the curve is below the x-axis. So if we come across to our graphics calculator and then we go through the process of finding the definite integral, so it's x squared take 1 between 0 and 1, and we get a negative number, we get minus 2/3. So we can say that's minus 2 on 3. So the area must be equal to the negative of the definite integral, because we'll then get a double negative, and so it will be a positive. So it'll be negative of negative 2/3, which is then just 2/3 as is. Okay, so we can notice that definite integrals can be negative. But, as we said before, areas cannot be negative. So that means that we have to work out how we're going to get around this. But before we do that, we can see that this implies that definite integrals are just simply numbers. They aren't directly areas, but they are simply numbers which can be interpreted as areas, or they can be calculated from known areas. So there's a strong link between definite integrals and areas, but they're not exactly the same thing. So if we look at this function here, the function's below 0 between these two lines. So this is the line x equals a, and this is the line x equals b. So the area bounded by the curve, the x-axis and the vertical lines is given by the negative of the definite integral from a to b of f of x dx, or the integral is equal to the negative of the area. So there's these two key formulae that we pick up that are going to be useful. Okay, alright, so if we have a look at this function here, we've got known areas that we can work with. So we've got to evaluate the following definite integrals using an interpretation of areas as standard shapes. So the integral from 1 to 3, well, here is 1, halfway between 1 and 2. Here is 3, halfway between 2 and 4. So we've got a rectangle, and it may be hard to see, but that's a height of 2. So the area of the rectangle is equal to the definite integral because g of x is greater than 0. So we can say because g of x is greater than or equal to 0, the integral from 1 to 3 of g of x dot dx is equal to the area, which is equal to 2 times 2, which is 4. Now, if I said units squared, I'd be talking about area, but because I'm getting a definite integral and it's just a number, I leave it as 4. So now we've got the integral from 3 to 7, so we can see out here is 7, and this is a little hard to see, but it's a circle with the center at 5. So we go 2 this way, we go 2 this way, and this is minus 2 down here, so that's 2 down there as well. So radius is 2, so half a circle. So we can say because, now in this case the function is less than 0, so the integral from the 3 to 7 of g of x dx is equal to the negative of the area, which is equal to negative pi r squared on 2. So it's negative pi times 2 squared on 2. So it will be, well, that's 4 pi on 2, so it'll just be negative 2 pi. And again, I don't put units squared because it's simply just a number. And that's what the note says here. So no units are given and negatives are acceptable. Now we've got to calculate the area between the graph on y equals f of x between 0 and 7. So 0 is back here. So we've calculated this bit, we've calculated this bit, we just need the area of the triangle. So we can say because g of x is greater than or equal to 0, the integral from 0 to 1 of g of x is just equal to the area, and the area is half the base times the height, so it's half 1 by 2, so it's just 1. So that's my integral. So then the integral from 0 to 7 of g of x is going to be the integral from 0 to 1 of g of x plus the integral from 1 up to 3 of g of x. And now, because we want area, we're going to have to subtract. So we're going to subtract the, and I should say, instead of calling this the integral, this is really going to be the area. So the area is equal to the positive integral from 0 to 1 plus the positive integral from 1 to 3, and then we're going to be adding the negative of the integral from 3 to 7. So in that case, we're going to be subtracting a negative number, so we'll be adding. So then it's 1 plus, now 1 to 3 was 4, take minus 2 pi, and so then it becomes 5 plus 2 pi. And in this case I give units because we're finding an area. So when we're doing area, we're adding integrals where the function is positive and subtracting it where the function is negative. So in general, the area in this case would be equal to the integral from the negative of the integral from 0 to a of f of x plus the integral from a to b of f of x, take the integral from b to c of f of x. Okay, so we also have some key properties of the definite integral, which we can see in terms of area. So if we have a function, could be any odd function, and I say I'm looking, and we'll say for the moment that it's positive. So the first thing that we can say is if we are going and finding the area from A to A, so it's the area below that one point A. So there will be no area, so it will be 0. If we go from A to B of negative f of x, so let's say it reflects in the x-axis, well, that'll give us a definite integral in this case that is below the x-axis, and so it will just become the exact same value, but it will just be the negative of the definite integral. Now you might say, well, that's only one case. What about if the function was below? Well, if this was f of x here and we were doing negative f of x, then it would just swap to the top, and then we would get a negative of a negative integral, which would become positive. So it would still work. If we have any number out the front, or multiplied by the function, a bit like what we can do with derivatives, we can bring it out the front of our definite integral. If I'm adding from a to b, and then from b to c, like this, then the integral is just going to be the combination of both those areas, so it's going to be equal to the integral from a to c of f of x. And then if I'm doing two functions added together, I can split that up. So if we think a little bit about two functions, let's say I had another function up here. This was my a point, this was my well, let's in this case call it my b point. If I have the integral from f of x here, and then the integral of g of x will be all the way up there, then f of x plus g of x would be all the way up here, something like that. And so then the integral of f plus g would be all of this area, but we could just find that by adding individuals. So I could go a to b of f of x plus a to b of g of x. And we'll do an example of that in class. So we can use then technology to find these following definite integrals. So the integral from 1 to 2 of x squared. Well, if we just use our calculator, we know that it's math and then across to this one. So x squared from 1 up to 2 gives me 7 on 3. It's always good to keep things as a fraction because it's more exact. Then if we do the same thing from the definite integral of 1 on x, then in this case it's 0.693. There's no way we're going to be able to keep that exact, so we'll just go 0.693 and we'll go to one more decimal place just in case they want it exact, so 6931. Okay, so now we've got to find the integral from 1 to 2 of x cubed plus x cubed plus 1 on x. So the integral from 1 to 2 of x cubed plus 1 on x is equal to the integral from 1 to 2 of x cubed on x plus 1 on x. Now that's just x squared, so that's the integral from 1 to 2 of x squared plus 1 on x. And using our rule, we can say that our last rule that we looked at, we can say that's integral from 1 to 2 of x squared plus the integral from 1 to 2 of 1 on x. And so then it's 7 on 3 plus 0.6931, and then I'm just going to have to, so pausing it to just go to find the value, we find that it gives us 3.0264, so 3.0264, which equals 3.026. That's the 4 significant figures. So just because sometimes in these questions they ask for more than just a basic 3 significant figures. So because that's an integral, there's no need for units. Okay, if the integral from minus 1 to 2 of g of x equals 8, and the integral from minus 1 to 8 of g of x is 2, find the integral from 2 to 8. Well, we know that the integral from a to b of g of x plus the integral from b to c of g of x is equal to the integral from a to c of g of x. That's what we're going to use here. So using it in this situation, we can say the integral from minus 1 to 2 of g of x plus the integral from 2 to 8 of g of x is going to be equal to the integral from minus 1 to 8 of g of x. We're looking for this one here. This is what we want. We know from minus 1 to 2 it's 8. So 8 plus the integral of 2 to 8 of g of x dx, and we know from minus 1 to 8 it's 2. So then if we move the 8 to the other side, we'll say the integral from 2 to 8 of g of x is 2 take 8, which is minus 6. So this g of x must have at least some region below the x-axis to get an integral of minus 6. But that's all well and good, but then how do we do it exactly? How do we actually algebraically calculate the definite integral from any function? So that's where we're headed next. We know how to work with it when the function's above and below the axis. We know how to do it on a calculator. But for those times when we have to do it exactly, how can we actually do that? And that's where we're headed next time. Okay.